Hello and welcome back to the next module of our course. We've just wrapped up that digit classification exercise from our last module, where a neural network learned how to recognize handwritten numbers. Now you might wonder, how do we move from teaching a network to recognize digits to something more advanced, like enabling it to understand and process entire sequences or paragraphs in a language? This unlocks endless new possibilities, because language is at the heart of how we communicate, learn, and share knowledge. The answer lies in a practical and elegant approach, training the model to predict the next word in a sequence of words. Why this approach? Predicting the next word forces the model to learn how words relate to each other, capturing both immediate context, so the words just before it, and broader context, like the structure and meaning of the entire sequence. This task is both challenging enough to encourage rich understanding and generalizable enough to apply across countless language based tasks, from translation to summarization and beyond. For many years, researchers experimented with various neural network designs, like recurrent neural networks, long short term memory networks, and bidirectional models. They tackled text based problems such as language translation. However, these approaches struggled with two key challenges. They found it difficult to capture long range context, and their architectures required ingesting text sequentially, one word at a time, making them slow and hard to scale efficiently during training. A breakthrough came in 2017 when a team at Google introduced the transformer architecture, a model specifically designed to overcome these training limitations. Unlike earlier methods, transformers process entire sequences in parallel during training, thanks to their revolutionary attention mechanism. This allows for faster, more efficient learning, enabling transformers to be trained on massive amounts of text data while still capturing long range relationships effectively. And what's astonishing is that from that moment on, no fundamentally superior architecture has come along. The transformer is, quite simply, the backbone of nearly all our state of the art AI today. Let's have a high level overview of how a transformer works. Let's say you want to feed to a model a sentence or a passage. The first thing it does is break the text into small pieces called tokens. Now, these tokens aren't always just single words. Sometimes they're fragments of words. Sometimes a token might be a punctuation or a really common combination of letters, like ing. You can imagine this as chopping your sequence into puzzle pieces. Each piece is then converted into a numeric representation known as an embedding. This embedding is essentially a long list of numbers that you can imagine as coordinates in a high dimensional space. Don't worry about the high dimensional part. Nobody can really get it. It's impossible for us. The dirty secret is to just imagine a three-dimensional space and scream high dimensional. Simply put, words or tokens with related semantic meanings tend to add up with similar embeddings, like words fast and quick. Conversely, a rock concert might land far away from rock formation, even though both use the same word rock. In more traditional neural networks, we'd pass these embeddings one step at a time. But the transformer is different. It takes the entire set of tokens in parallel and updates their numeric representations by letting them talk to each other through a mechanism called attention. Attention is the heart of the transformer. It's a special process that allows each token to figure out which other tokens in the sequence are most relevant, like if rock should associate more strongly with concert or with formation. That context rich information travels back and forth, adjusting these embeddings so that each token encodes a more precise meaning in the presence of all the others. Meanwhile, a multi-layer perceptron, something very similar to what we've seen in simpler networks, transforms these embeddings further. You can think of it as repeated cycles of looking around at the other words, figuring out what's relevant, updating the meanings, and then applying a deeper neural network layer. After a series of these attention plus perceptron layers, and we will cover them in detail later, the transformer emerges with a highly informed representation of every token. Then, to predict the next token or word in a sequence, it takes the final representation of the last token in the sequence and uses that to generate probabilities for all possible next tokens. Because these probabilities are just that, probabilities, then transformer can give slightly different answers on different runs, especially when you allow it to pick less likely but still plausible words. So, yes, the model is deterministic at its core. It always calculates the same options for the next word given the same input. But when you use a method to pick from those options randomly, like rolling a weighted dice, you can get slightly different answers each time. This makes it feel more like it's guessing, even though it's following clear rules underneath. We'll cover that part in more detail later on in this module. Once a token is selected, it's added to the sequence and the process repeats, token by token, until the entire output is generated. As you might recall, learning in neural networks primarily involves computing the error between the network's predicted output and the actual output from the training data. In the case of text models, this involves calculating the loss between the next token predicted by the model and the actual next token in the text. And that's not all. Transformers don't just do text. They form the basis for advanced models that handle images, code, and speech. But in every case, it's the same foundational mechanism established in 2017 that's making it happen. Parallel processing of inputs, embeddings that capture meaning, attention that spreads context through the data, and multi-layer perceptrons for deeper transformations. In the next video, we'll dive more deeply into how attention actually works. We keep saying that attention is the magic that drives the power of transformers. But what does it actually mean in practical, down to earth terms? Let's walk through a simple example. Picture a sentence: a shiny red car sped through the bustling street. We start off with embeddings that capture each word in a broad, generic sense. Right now, car is just car and red is just red, without much nuance. But the transformer wants a richer understanding. If car is described as shiny and red, it ought to move into an entirely different part of the conceptual space compared to if it was rusty and broken. That is where attention steps in. You can imagine that each token gets to look around at its neighbors and figure out who's relevant to me and in what way. The word car, for instance, might glance over at shiny and red and think, these adjectives are describing me. I should soak in their meanings. Meanwhile, words like the or bustling might be less relevant to car in that moment, so the model politely tunes those out. Now, behind the scenes, each token is equipped with a little numeric representation of a question, of what's called queries, and an answer, often called keys. Picture each word sending out little signals that say, I'm looking for adjectives, or I'm an adjective that modifies nouns. If car has a question like, which adjectives belong to me? Then shiny and red respond with, we're adjectives, right here, and they get singled out. Finally, the model takes the meaning from those adjectives, packaged up as yet another numerical representation, the value, and adds it directly into the embedding of car. That's how car transforms through a generic sense to a more vivid, context aware notion of a shiny red car. The same logic applies in far more nuanced settings. Maybe you're reading a mystery novel and the model is figuring out who the detective is, who the suspects are, and who the victim might be. Each token asks around, gathering information that might live far across the page. And crucially, this is all done in parallel, rather than slogging one word at a time. That's a big reason transformers can handle huge sequences of text so efficiently. Everything updates together, thanks to attention. Transformers apply this attention step over and over across multiple layers. At first, words pick up small details like adjectives or simple grammar. In deeper layers, the context becomes richer and more abstract. If the word is rock, does it refer to a rock concert, a rock formation, or something else entirely? The model refines that meaning each time it runs this attention exchange, letting synonyms, positions, or previous sentences weigh in. It's a lot like having a huge committee, each member with a slightly different perspective, voting on how each word should shift in meaning. In the end, what you get is a powerful mechanism that builds a really nuanced understanding of language. By the time the transformer finally predicts the next word, it's not just throwing out a random guess. It's drawing on everything it's learned about how context changes meaning, storing relevant bits of information in the embeddings, and focusing precisely on the tokens that matter. All of this is crucial for tasks like translation or question answering. If you ask, what color was the car? The model should zero in on the adjectives shiny and red, ignoring other details like bustling street. If you ask, what type of rock do you listen to? It might pay attention to the word listen to avoid confusing them with a rock formation. Everything is context driven, a dance of focusing on the most relevant bits of meaning hidden across the text. The math underneath transformers is elegantly designed for parallel processing on modern supercomputers, which is part of why these models got so big, so fast, and why they work so well. But the core intuition is that each word learns to look around and figure out who to listen to, giving you the text embeddings that aren't just about the word itself, but about its whole context. In the next video, we'll talk a bit how transformers store all these learned facts in their layers, and why you never get exactly the same answer. If you type in "the Mona Lisa was painted by," your large language model confidently completes Leonardo da Vinci. It's obvious the model knows that Leonardo da Vinci is the artist behind the Mona Lisa, but how exactly does that knowledge get stored? If you remember from our earlier videos, all the stuff a language model knows lives inside billions of numerical values, or weights. These weights are like giant lookup tables, fine-tuned for training like little dials. This is exactly what we covered in the previous module. Same principles apply. They tell the model how to process input, combine context, and recall facts. While attention helps decide which part of the sentence matters in the moment, the actual facts seem especially tied to a specific part of the model, the multi-layered perceptrons, or MLP blocks. It is quite similar to the digit classification neural network we covered before. Information flows through a transformer through an attention block, followed by an MLP block, then another block of attention, another block of MLP, and so on and so on. But why MLPs? Because the majority of models' weights live there. When an input like Leonardo da Vinci flows through the MLP, the weights in these layers act as a huge network of connections. These weights essentially decide how to nudge the numerical representation of Leonardo da Vinci towards the Mona Lisa direction. You can think of it like this. If the embeddings are the input, the weights in the MLP are instructions that say, whenever you see these specific patterns, connect them to this fact. MLPs are incredibly powerful because of their sheer size. With so many parameters, they're like a massive library, capable of storing an astonishing amount of knowledge. When a model learns during training, it's as if it's filling in this library with instructions like, if you detect Leonardo da Vinci, light up the Mona Lisa related directions. Of course, it's never just a simple one weight equals one fact. Instead, the knowledge is spread across thousands of weights, intertwined with other information. These layers act like the model's memory, where facts about people, places, and things are stored in a way that the model can recall when needed. In the next video, we'll talk more about why an AI model might not always give the exact same answers, even for well-known facts. Imagine you give a language model a prompt like, "Tell me a story about a flying cat," and it responds with a quirky little narrative. Then, moments later, you ask for the same story, but this time it's different. Why did it change its answer? Isn't it supposed to be the same model, trained on the same data? The short answer lies in the fact that these models generate text probabilistically. Think of probability as a measure of how likely something is to happen. When a model predicts the next word or token, it doesn't settle on a single definite choice. Instead, it assigns a probability to every possible next token. Car might have a high probability, hippopotamus a much lower one, but nothing's off the table entirely. This design is on purpose. For many tasks, for instance storytelling or creative writing, you don't want the model to spit out the same exact words every time. Randomness can foster originality. It is what keeps AI response from sounding like a broken record. If you wanted the model to answer with absolute consistency, you could force it to pick the highest probability token every time, but this can lead to dull, repetitive text. That's where the concept of temperature comes in. Picture each prediction like a set of dice rolls weighted by probability. A high temperature means the model is more willing to choose those less likely tokens. It's like rolling dice that can land on unlikely faces more often, injecting excitement and variety. Meanwhile, a lower temperature sticks closer to the safest bets, making the output more predictable and repetitive. Of course, the upside of randomness is creativity, the downside is hallucinations. A model might guess the next token that sounds convincing, but is factually off. Maybe it claims the flying cat also built the Eiffel Tower in 6082. Pure nonsense, but within the model's realm of possible completions. That's not because it wants to lie, it's because it's always drawing from a wide probability distribution over words. It is an assumption in the design of the algorithm. Sometimes, improbable tokens slip in, and if the context doesn't steer it back to reality, it can just keep building on that fiction. This is why you sometimes see disclaimers about these tools, warning about potential inaccuracies. The same mechanism that can stitch together creative or nuanced responses can also lead to confident but incorrect statements. Adjusting the temperature is one way to manage this. A lower temperature often means fewer wild guesses, which can reduce hallucinations. But you also lose some of the natural flair or spontaneity that makes these models fun to interact with. When a model's answer changes with each try, think of it as a roll of highly sophisticated dice beneath the surface. Instead of locking into one fixed response, it explores a range of plausible outcomes, creating room for variety, creativity, and yes, the occasional curveball. This dynamic approach is what makes these models so versatile, and understanding the probabilities behind it can help you harness their power while knowing when to give their answers a second look.